Bikasa, am I audible?
Yes, ma'am, you are audible, ma'am. You are audible.
Okay, thank you, sir. Warm good morning to all. Welcome you all in this 5 days FDP, which is supported by Atal Initiative of AICT. This program is going to provide platform for researchers all over the country to upgrade their research ideas in the field of nano devices and advanced nano material. I would like to request Dr. Bikash Sharma sir, coordinator of this FDP, to kindly address the beginning of this 5 days FDP.
Very good morning to one and all present over here. We warmly welcome all the participants, our esteemed guests and delegates to this 5 days Atal FDP program on nano devices and advanced nano materials. To say that, firstly, I would like to warmly welcome our chief guest, Professor Dr. Gurdaman Lal Sharma sir, our director SMIT, our guest of honor, Professor Chandan Kumar Sarkar sir from Jadavpur University. We are very honored to have you two as our guests and our delegate to this inaugural session. Thank you very much, sir. We humbly express our gratitude to both of you for sparing your time and gracing this occasion and motivating us. We are highly motivated, encouraged and motivated by your presence. Thank you once again, sir. Just for the information that it has really been a very overwhelming response. We have received about 120 registered participants from across India. And to mention that, we have a lot of participants from IITs, triple ITs, NITs, right across the country, from many northeastern states to right back to Rajasthan, Gujarat, Haryana, Tamil Nadu, Kerala, Andhra Pradesh, Odisha, Bihar, UP. I should say it's a pan-India participation that we have received, and we are very honored and grateful to all the participants who have registered themselves to this particular FTP. We also like to thank AICT and the Atal Academy for their support and considering us and sanctioning this particular Atal FDP for our for this 5 days, which will be from 6th to 10th of December. We have a list of eminent speakers from academia and industry who have agreed to deliver their talks and enrich us and all the participants in this regard, on this particular area of nano devices and advanced nano materials. Just for information, I would like to say that the topic that we are actually having is a very specialized topic, that is nano devices and advanced nanomaterials. Despite it being a very specialized topic, we have got really good participating numbers, because the maximum limit what Atal permits is 200 number of participants, and we have received 120 participants, so that's very encouraging for us. So with this note, I once again thank our Honorable Director, sir, Professor Gurdaman Lal Sharma, sir, and our guest of honor, Professor Chandan Kumar Sarkar, sir, to grace this occasion and to encourage, motivate us as well as the participants for this 5 days Atal FDP. And once again, a big thank you to all the participants who have made it convenient to attend this 5-day FDP. And we hope that it'll be a very enriching session to all of you with the expertise and the experience of our learned speakers that we have for this 5 days. There are altogether 14 speakers that we have from IITs, Jadavpur University, from industries like Qualcomm and Global Foundries as well. So thank you once again and welcome you all. Have a very good day and a very good learning session all these 5 days. Thank you, everyone. Thank you, Riji ma'am. Over to you.
Thank you, sir. Thank you so much. Now I would like to invite Head FDC SMIT, Dr. Om Prakash Singh, sir, to address the session.
Good morning, Reggie. I am audible to.
Yes, sir. Yes, sir.
Okay. A warm welcome to one and all present here. Honorable Chief Guest of today's inaugural function, Professor G.L. Sharma, Director, Sikkim Manipal Institute of Technology. Respected Guest of Honor, Professor Chandan Kumar Sarkar, Jadavpur University. All Associate Directors, SMIT. HODs, Distinguished Resource Persons from higher educational institutes and industry, my fellow colleagues, dear participants, and members of the organizing committee, ladies and gentlemen, good morning. It gives me immense pleasure to welcome you all to the inaugural function of the online Atal FDP on nano devices and advanced nanomaterials. This 5 days FDP will be conducted with effect from December 6th to 10th, 2021. Under the umbrella of Center for Faculty Development, Sikkim Manipal Institute of Technology, various faculty development programs have been successfully conducted. Even in this pandemic situation, over a year, a significant growth was noticed in terms of number of FDP, STTP workshops organized, planned, and number of participants. I am happy to announce that under the leadership of Director SMIT, the Center for Faculty Development has trained about 1,500 participants on various current topics such as artificial intelligence, Python programming, NEP 2020, outcome-based education model, technological leadership, Internet of Things in last 6 months. The best part of the training conducted by SMIT is it is absolutely free of cost to in-house as well as external participants. The theme of this Atal FDP is nano devices and advanced nanomaterials. Nano devices play a significant role in semiconductor industry and the potential demand for such devices is higher. Devices fabricated at the nano level provide a larger impact in improving the health of human beings, energy consumption, pollution control, and many more. In the broadest sense, nano devices allows researchers to exploit the technical capabilities of electronic, magnetic, mechanical, and biological systems. The best example of nano devices are at present clearly associated with the Internet of Things industries, where potential for such devices is much broader due to use of nano battery systems that can be extended the lifespan of IoT device. For effective design and fabrication of devices at the nanoscale level, definitely good choice of nanomaterials are required. I hope the technical sessions on various topics on nano devices and advanced nanomaterials would benefit the participants to a great extent, and the expertise of the resource person drawn from different higher educational institutions and industries, to name a few: IISc Bangalore, IIT Roorkee, IIT Guwahati, Jadavpur University, IIST Shivpur, Makaut West Bengal, Kalyani Government Engineering College, West Bengal, North Bengal University, Sikkim University, Semiconductor Integrated Device and Processing Lab, Hostek, South Korea, Qualcomm Bangalore, and Sikkim Manipal Institute of Technology, Sikkim, will benefit the participants from different parts of the country to a great extent. I take this opportunity to congratulate Dr. Vikas Sharma, Associate Professor, Department of Electronics and Communication Engineering, coordinator of the Atal FDP, for taking initiatives and materializing the program during this pandemic situation. I would also like to express my sincere thanks to all esteemed resource persons for acceptance and delivery of lecture to this program. On behalf of SMIT and Center for Faculty Development, SMIT express my gratitude to Honorable Chief Guest and Guest of Honor for sparing their valuable time to encourage us and participants. I also thank the organizing team for their efforts and hard work to bring this FDP to reality. I also request the participants to actively take part in training program and get benefited from expertise and experience of the resource persons. With these few words, myself, Dr. Omprakash Singh, Head Center for Faculty Development, SMIT, would once again welcome each one of you to this FDP. Wish you all a safe and healthy times. Thank you.
Thank you, Om Prakash sir. Now I would like to have the honor to invite guest of honor, Professor Dr. Chandan Kumar Sarkar sir from Jadavpur University to kindly address the inaugural session.
Okay. Is it I'm audible now?
Yes,
Hello.
sir, you are audible.
First of all, I say good morning to everyone, including participants and dignitaries who are present in the associated with this FDP. And I'm also happy that I am being invited for such a August gathering. Just now you heard from Professor Singh, he mentioned that this area of nanotechnology has been grown like anything, and particularly in communication. And apart from the communication, there are many areas where nanotechnology and nanomaterials are really doing a wonderful, I would say, wonderful job. And anyone who will be knowing about little bit about nanotechnology, you know, there is a vast domain. The nanotechnology and nanomaterials are available. Myself is more interested in semiconductor of nanotechnology, particularly very large scale integration. As you know, the integrated circuits play a very important role as far as present day technology, or you can say communication or anything. And this way, the nanotechnology has a profound effect in our life, and it is something is getting important over the years. So for this purpose, I would really think that this workshop or this FDP is very useful for people who will be attending it. And I understand many people from different premier organizations, they are the speakers for the conference and for this FDP. I'm sure they will have very good deliberation which will benefit the participants, because this is the area I personally feel that this has a lot of future and implications in many developments in future. So this way, the nanotechnology and nano devices are the area which are also being studied very well in various institutes, not only in India, also in abroad. So we can have a very good collaboration with the different institutes within India and as also abroad, which will benefit us from basic knowledge of this area. So before I finish it, I would like to thank all the authorities of SMIT taking trouble in organizing this FDP, I think, which is not only beneficial to your faculty, it will be beneficial to faculties from other institutes, and also inviting people from all over the country. And hello, can you hear it?
Yes, sir.
Yes, sir. Yes, sir. Yes.
So what I feel that this is very much beneficial for everyone, this FDP, and I, with these words, I would like to wish you all the best and success for this FDP which you are organizing. Thank you very much.
Thank you, sir. Thank you so much. Now I would like to have the privilege to invite chief guest of this FDP, Professor Dr. G.L. Sharma, sir, Director, SMIT, to kindly convey the inaugural session.
Yeah, good morning, ladies and gentlemen. Hope I am audible.
Yes, sir. You are audible, sir.
Yeah, good. Well, at the outside, I would like to extend a very warm welcome to our guest of honor, Professor Chandan Kumar Sarkar, all our associate directors, my esteemed colleagues, and last but not the least, our participants who are definitely going to be benefited from this particular FDP. I know the pandemic has prevented us from having it offline, And our endeavor in the days to come would be to have this kind of session in a hybrid mode. We will not only keep it in offline, because at times what happens is when we organizing something, some people are really not able to travel, but then it is essentially that when you meet one to one, and when you are going to discuss something that is going to be there in the days to come, and especially advanced nanomaterials, which are going to really make a lot of difference in our lives. And it's better that people can interact one to one in person, and take it forward collectively, because the combined wisdom would definitely lead to exponential growth in the field. So this is one of our endeavor. But first, let me, again, also welcome all our speakers, those who are going to be there. I see that there are 14 speakers who will be speaking, like Professor Kumar Sarkar, who is, ATC department from Jadavpur University. Then we shall have also Professor Brajesh Kumar Kaushik from IIT Roorkee, Professor Sanjeev Kumar Shrivastava, he is from ISC Bangalore, Professor Roy Paily, he is from IIT Guwahati, and Professor Sudev Gupta, again from IIT Roorkee, Professor Hafizur Rahman from IST Shibpur, and Professor Debashis Day, School of Computational Science, Macau, and Professor Angsuman Sarkar from KGEC, Professor Somnath Chatterjee from our own Center of Nanotechnology, SMIT, Sikkim, Professor Sanjoy Dahal, Sikkim University, Professor Writam Banarjee, Postec, South Korea, and Dr. Chandan Ghosh from Jadavpur University, Dr. Amretashis Sengupta, sub-scientist NBU, and Mr. Pragnjit Datta Roy, again from Qualcomm, Bangalore. So the galaxy of speakers, I can see that a lot of discussion, a lot of deliberations are going to be there, and our participants will be highly benefited. But now, if you look at it, that this nanotechnology, this is one of the fields, like ladies and gentlemen, we can always say what we have seen once upon a time when we used to have those, mainframes, maybe of 4 GB data, or GBs were never even MB data. So there is a full, maybe 20 by 12 feet room where you have this kind of thing, and this nanotechnology has made it that you are carrying a phone, maybe which has capacity of 256 GB. So this is what has been the effect of this nanotechnology, and it is one of the most promising field of 21st century. And the ability to convert basically nanoscience theory to useful application by observing, measuring, manipulating, assembling, and controlling, and manufacturing things at nanoscale have really brought about a huge difference in our daily life. And now this is not only, the area is not limited only to some certain field. It is applicable equally to chemistry, to biology, to physics. Of course, material is one of the thing, and any other engineering application which we have. So if we talk about pre-modern example of nanotechnology, how it has evolved. So if you see the Lycra's cup Rome, this is one of the example of dichroic glass, wherein this colloidal gold and silver in glass allows it to, look opaque green when lit from outside, but translucent when it is, light shines through inside. another maybe 19th to 17th century. Why I'm going just discussing this is that this is one of the field which people have been thinking for long, and started right from the 4th century, and then we in 9th to 17th century you had those glowing and glittering luster ceramic glazes. Those are used in Islamic world, and later in Europe, which contain silver or copper or other metallic nanoparticles. Even from 6th to 15th century, you another had those vibrant stained glass windows in European cathedrals, which owed their rich colors to nanoparticles of gold chloride and other metal oxides. And if you have another example from 13th to 18th century, Damascus, that saber blades contain carbon nanotubes and cementite nanowires. So guys, these are the all example where people have been working, and it has really brought about a huge change how we look at things. Now, how it started, basically the idea and concept behind this nanoscience and nanotechnology, it started with a talk that was entitled There is a Plenty of Room at Bottom by physicist Richard Feynman, which has held at an American Physical Society meeting at California Institute of Technology on December 29, 1959, long before the term nanotechnology was used. And he has mentioned and described the process in which scientists would be able to manipulate and control, individual atoms and molecules. And over a decade later, in his exploration of ultra precision machining, Professor Norio coined the term nanotechnology. And it was not until 1981, with the development of the scanning tunneling microscope, that could see individual atoms, that modern nanotechnology began. So nature already does nano. Now how? In nature, there are numerous examples that we come across of nanotechnology based systems, and these are already highly optimized through millions of years of evolutionary development. The inner ear of a frog, left, if you say, has mechanical cantilever that measures the direction deflection as small as 3 nanometer due to sound. The male silk moth, that is middle, can detect with single molecule precision the pheromones of a female moth emitted up to 2 miles. The eye of an ant, that right eye, uses nanoscale features to greatly enhance its visual sensitivity. And recently, the wings of a butterfly were shown to be intricately colorful because of nanoparticles that act as a photonic crystal. So now, guys, like I don't want to go into this, basically the possible uses and application of nanotechnology. It could be, in detection, wherein if we could detect molecules with same level of sensitivity, selectivity, and energy efficiency of silk moth, we would be able to dramatically improve a vast array of crucial national and international needs, from homeland security to environmental monitoring to edible oil. And maybe energy, the impact of nanotechnology on both energy generation and storage is likely to be enormous. The most prominent areas of research in employing nanotechnology for energy uh, includes the development of cheaper solar cells and new low water consumption plants for biofuels, photoelectrical chemical cells that could efficiently convert sunlight into hydrogen, higher energy density and faster charging batteries, and of course the old favorite, hydrogen storage. And few other fields, like when it comes to maybe nano medicine, nano dentistry, nano diagnostic, and many more. So, guys, like ladies and gentlemen, I am not dwelling too much into it. I know the galaxy of these experts would be speaking, and we all will be immensely benefited through their talks and their experience. My request to you all would be that this should not finish here. Please have those interaction going on even after this FDP, and see to it that how you all can come together and apply your brain, because I keep saying that 1 and 1 is not 2 but it is 11. Your strength suddenly increases. So this is what I expect, that you will be immensely benefited from this workshop, and would also able to see how what exactly is happening and what more you can do, and come together to bring about an appreciable progress further into this field, which is already doing very well. So with this, I would like to congratulate FDP cell, Atal FDP cell of SMIT, wherein from their report I could hear that 1500 participants have been trained in different areas of cutting edge technology, and this has been free in house. So I once again take this opportunity to congratulate Dr. Vikas and Dr. OP Singh and all the team members who have made this FDP possible, and wish it a great success, and thank all the speakers and participants for coming together to benefit from each other. Thank you very much.
Thank you, sir. Thank you so much. Now I, Rijide, on behalf of the entire organizing team of this FDP, extend a very hearty vote of thanks to our guest of honor, Professor Dr. Chandan Kumar Sarkar, sir, from Jadavpur University, for his vital appearance to grace this occasion. Sir, thanks a lot. It really means a lot to us. We are grateful to our chief guest, Professor Dr. G.L. Sharma, sir, Director SMIT, for his graceful presence. Sir, thanks a lot for giving us precious time in your busy schedule. My heartfelt thanks to Chief Patron, Lieutenant General Dr. R.S. Grewal, AVSM, VSM, Vice Chancellor, Sikkim Manipal University, Sikkim, for his constant support and guidance. I owe special gratitude to our patron, Professor Dr. K.S. Sherpa sir, Registrar, Sikkim Manipal University, Sikkim, for his cooperation and guidance. We are grateful to our esteemed speakers for accepting our invitation and sparing their invaluable time to enlighten us with their commendable talks. Professor Dr. C.K. Sarkar sir, Jadavpur University, Professor Brajesh Kumar Kaushik, EC Department, IIT Roorkee, Professor Sanjeev Kumar Shrivastava sir, iSTEM CE, NSC, IIC Bangalore, Professor P. Roy Paily sir, EEE, IIT Guwahati, Professor Sudip Dasgupta sir, EC Department, IIT Roorkee, Professor Hafizur Rahman sir, IT, IIEST Shibpur, Professor Debashis sir, School of Computational Science, Makot, Professor Angsuman Sarkar sir, EC, KGEC, Professor Somnath Chatterjee sir, CMSMT, SMIT, Professor Sanjoy Dahal sir, Sikkim University, Dr. Writam Banarjee sir, SIDP Lab, Post-Tech, South Korea, Dr. Chandan Kumar Ghosh sir, Jadavpur University, Dr. Amretashis Sengupta, ACRB Scientist, NBU. Lastly, Mr. Pragnjit Datta Roy sir, Qualcomm, Bangalore. Thank you all. I take the opportunity to thank all the participants who joined the FDP from different destinations to upgrade their research ideas and developmental activities in nano devices and advanced nanomaterials. I may also express sincere thanks to AICTE for sponsoring the FDP, which intends to give critical insights to the latest research and developments in the area by experts from academician and industry persons. Last but not the least, it is my privilege to propose a vote of thanks and acknowledge the contribution of all the organizing members who are working hard day and night to make this FDP a memorable success. Once again, I thank all for your kind attention. Thank you. I would request all the participants now to stay here as the first enlightening talk by Professor Dr. C.K. Sarkar sir will start shortly. Thank you all. Over to you, Vikas sir.
Thank you, ma'am. Thank you so much. Once again, I would like to thank our honorable chief guest, Professor G.L. Sharma sir, Director SMIT, our guest of honor, Professor Chandan Kumar Sarkar sir from Jadavpur University, who has also been the ex-dean, former dean of IIEST Shivpur, formerly known as Bengal Engineering College. And all the participants and delegates who have attended the inaugural session. Thank you once again. We will shortly start with our first technical session or the first plenary talk by Professor Chandan Kumar Sarkar sir in couple of minutes. CK sir, I have made you the presenter. You can go ahead. I'll play your slide, sir. Hello, sir. Yes, sir. Sir, I have presented your site. Sir, you can start, sir.
Okay. Okay. Can you make it bigger? Hello?
Sir, this is full screen.
Okay, let me. This is a full screen?
Yes, sir.
Now,
Yes, sir.
yeah, it is. Okay. So shall I start?
Yes, sir, sir. Sure, sir. Please, sir.
Very good morning to everyone. Still it is morning, so I'm not wrong if I say so. So this is the title of my presentation is Introduction to Electronic Nanotechnology. And I will be presenting some of these issues, particularly the influence of nanotechnology in electronic and electronic devices and also materials. Next one. Okay, the outline of the talk is what is the electronic nanotechnology? That is the main concern I have here. Now, on the basis of the electronic nanotechnology, how you have the electronic nanoelectronic devices, because these devices dimensions are very small, so we normally refer to as a nanoelectronic devices. And these nanoelectronic devices, the way it has been developed, it is now showing some different future. I mean, different future in the sense that some new ideas are coming with these new nanoelectronic devices. In the nanoelectronic devices, more fundamental to is the nanoscale MOSFET. I'm sure everybody here among the teachers are all aware of MOSFET. The MOSFET is the key element for all the modern electronics. So how it will be changed when you apply nanoscale to these devices, make the MOSFET devices in the dimension of nanometer. So that is the issue here, how nano MOSFET influence the development of nanoelectronics. Now, I have taken up three areas here: carbon nanotube, which is one very well-known nanoelectronic device, or rather say nanoelectronic material. And then we have some solid-state nanoelectronic devices, which are coming very big way. And then final one is the molecular electronic devices. So these are some of the outlines of my present talk, which I have shown here. Next one. How the nanotechnology is defined, that is a very important. Nanotechnology is the understanding we controls the matter dimensions less about 1 to 100 nanometers. So you can imagine, which we are trying to understand through this nanotechnology. We want to explore the devices or matter in the range of 1 to 100 nanometer. And all the you have the phenomena which associated with these small dimensions like 1 to 100 nanometer. They show some interesting physics or interesting effect, which we are very much interested, because based on these interesting effects we can develop some new ideas and new devices which will be very important for coming day technology. Now, I've given some kind of idea many people will be having about nanotechnology, but still, what is the limit of the nanotechnology? And here you have, you know what nanotechnology is 10 to 1 billionth of the 10,000 thing, a number which is diameter is 10 to the power minus 9 nanometer. So this is the typical range or dimensions associated with the nanotechnology, and this is the what we are interested here in nanotechnology, going for this kind of dimension. once we go for this type of dimension, the difficulty is that the physics or the effects are very new to us, which were not observed before. So when we move to these nano dimensions, we do see a lot of effects which are different from the one which you have seen the larger dimension of the devices. So in that way, nanotechnology is very important in developing or rather predicting some new devices or new effects which can be utilized for future technology. Next one. Now, this is a slide which you can see there are some things which fall into the nanotechnology. You can see on my left, that is the things, natural the things which are observed in nano dimension. And then we have nanomaterials or nano devices, or I would say nano sort of these man-made nano systems, which are shown here. Some is the carbon nanotube and these DNAs, and these are some of the sort of classification of nano devices, things which are natural, things which are man-made. So this is the something which is one can broadly, you can present it to the common people, that how do you, and this is in the center we have dimensions of the different system or different materials which is constituting the nano effect. Next one. Now we have this thing, different classification, or rather I will say, broadly speaking, the different devices coming into different scales, which are here shown here. Now you have something called physical and chemical, and then you have this thing. This just very small, I cannot see it, that you can see this devices or this effect which are seen in the nano scale, which is, that's why I've said this is the importance of the scale. And now you have these effects which are, there is, you know, the systems which we have, and we have a technology, we have this other developments which are given the dimensions which are you can see in the upstairs, the upper part of the table. This is there. Okay, next one. Now, nanotechnology, as I said in the beginning, it's a really future of new technology. The future of this nanotechnology is very much important for many things. Now, you comes into the material science. There are powders, coating, and carbon nano materials, nanofabrics. So these are some of the materials which is given by in the falls into the nanotechnology. Then we have the energy aspects of this, solar power and photovoltaics, and there are a lot of nanotechnology applications are done in this energy sector. And then these are mentioned here. Then you have solar power and photovoltaics, and you have a solar cell developed with the nanotechnology, and which is now coming in a very big way. Now you have a medicine, one of the world very rather I would say very impressive or rather important area of the nanotechnology, because it has contributed quite a lot in the medicine. And this is a very sort of rather discussed or very well-known area of nanotechnology. People are interested in the medicine and biology or application of nanotechnology in biology. Then we have what we are mostly concerned in all the small nanotechnology devices, which are very much part and parcel of the computer, the NRAM, MRAM, and the quantum computation. So this nanotechnology governs that part in the electronics. Then we have a devices which can be fabricated with the various technology, which is here shown here, MEMS, some these AFM devices. So these are the applications of nanotechnology which have been listed here. Next one. Now, because of the computer, I think the nanotechnology has made a very big impact. The rapid increase in the transistor, because we have all these ICs which are made with the so many number of transistors put together, and this has created a very challenging for the many scientists, and that is a new area which everybody knows is a very large scale integration. So you want to put many transistors in one chip for various purpose, for having more functionality and more memory and other all sorts of things, and that has led to development of the computers, very fast computer that is something which have come out of the nanotechnology, particularly in computer. Then we are also by doing so, we are actually reaching to the physical limits. I tell you one few words that in nanotechnology, you want more and more devices to be put in your transistor in a IC chip. So when you want to put more and more devices, obviously you have to shrink the device size, and that is something very challenging. So you have the size is becoming a limit. Physical size becomes a limitation, and because of that, many new ideas we have to put so that it can be rather made applications. I mean, that is basically area of scaling in the IC technology, that you put more and more transistors in a chip, so you have a physical limit to that, and that one part. And then is that the fabrication process becomes very complex, and that is also a challenging. One thing I want to say here, that with the nanotechnology there is a lot of openings. I mean, as we see that we put more and more transistors in a chip, that fabrication technology becomes very difficult. But of course, if you have a difficult things, then it is not bad at all, because you have a problem how to solve it. So fabrication process is a very challenging process in nanotechnology. And as you know, with the people in physics background, that if you have a devices, the dimensions becomes very small. And normally we have a criteria of de Broglie's wavelength, that when the dimensions of the devices become comparable to de Broglie's wavelength of the electrons, then you cannot explain with the simple Newtonian mechanics. You have to apply some quantum mechanical rules. And that's why we say there is a quantum effects, and there are many devices which based on these quantum defects. And the quantum defects is a very crucial for small size devices. Quantum effects will be very important as far as the technology, nanotechnology is concerned. And once your dimensions becomes very small, then power consumption also becomes very large because a small dimension, the power dissipation becomes very large. So it is a very big concern. So we would like to do a lot of work how to solve this problem. So these are problems which are originating from the nanotechnology. So we have to have a remedy how to solve the power consumption problem in a small dimension material. And then you have the problem of speed. You want to have a computational speed should be also, and then you have a computational memory. These are the two issues which come very big way in nanotechnology. And then there is a increase in transistor density. As I said in the very beginning, scaling becomes a problem. What is the scaling? Basically, when you put these numbers, so many transistors, question is why you have so many transistors. The reason is that you want more functionalities, more memories, and also it becomes cost effective. So this is something which is very challenging, how to incorporate in more and more transistor, and then how to solve the problem of scaling. And the size, once you put so many transistors, then you reach to the nanometer technology, because your dimensions become very small, because you have to put so many transistors in a one chip in the order of billion. So that makes the knowledge, that makes that nanotechnology very crucial, particularly when you are going to that kind of dimensions. So that is very important. So I would say that these are the issues which are in the forefront of the nanotechnology, that you want to put more transistor in a chip, that consequence of that is that the dimensions of the transistors become very small. When the dimensions become very small, then there are a lot of effects which arises because small dimensions, like quantum effects, power consumption, and these are not a problem, because I would say these are really, it gives you openings for the researcher to look into it, like how to incorporate these effects in your device fabrication. Thank you. Next one. Now, one day, nanotechnology has, in the inaugural speech, the speaker has spoken that there are many areas the nanotechnology may be useful. But here we are having the mostly concerned with the nanoelectronics, how nanotechnology will be useful for nanoelectronics. Now, nanoelectronics development actually applies to electronic devices. That way it is that you want smaller transistors, smaller memory, and smaller circuitry. So these are the issues which would be the crucial in the nano technology applied to the electronics. And for that purpose, we have these devices which are predominantly useful for the nanotechnology devices, something like CMOS. Then we have memory devices and the switches. So these devices have to be fabricated in order to have the more nanoelectronic devices. I can say that this is the particularly area I'm interested, how the nanoelectronics will be useful for nanotechnology. This is for that you require these particular devices. They are very well-known devices there, but once you apply the nanoelectronics or nanotechnology, so these devices becomes quite complex. So this is something which as a researcher should look into it, like a modern development of CMOS, because now in the technology has given some sophisticated form of CMOS devices. Then memory, there is a lot of enhancement is required for memories, and also switches, that you want very fast switches. That one. Next one. Now I have given some small classification of emerging nanotechnology solution. What are the things? Now there are devices I've already told in the beginning when I introduced nanotechnology, because nanotechnology thing is that you are going for a dimension nanometer. When you are in the dimension nanometer, the size becomes very small. Then once your size becomes very small, then you cannot apply your classical concept, that Newtonian concept. Then your devices are based on quantum effects. So these are some of the quantum devices. For example, quantum dots, the size becomes very small, and some of you have studied the quantum dots. It's a really small dimension box. You confine the electrons in a small dimension, and which you may call it dot, or you may call it a box, and dimension of the box is maybe 100 nanometer. And once electrons are confined in the box, the behavior of this electron will be quite different from electrons which is in certain material. For example, if you take a quantum dot of 100 angstrom, what you will find, the behavior of this electron will be quite different from the electrons in a certain 1 micrometer device, or maybe more than that. The behavior is different, and this behavior leads to some new ideas and new devices. Then we have a single electron transistor, which is also another device based on quantum ideas. It really is basically tunneling effect, and tunneling is basically quantum mechanical effect, and utilized here to make certain device. And most important thing is, in single electron transistor, we are accustomed to MOSFET, where you have many electrons contributing. There are a lot of electrons flowing from source to drain. But here, single electron transistors, there is a single electron which controls the divide. That is the most interesting thing is that then we have a carbon nano field effect transistor. You make a field effect transistor using carbon nanotube. That introduction will come later, but I just simply give you carbon nanotube is nothing but a folding of a graphene sheet. If you take a graphene sheet, you fold it different way, you have a tube, and by having this tube you can have a different property of this material. And that's why carbon nanotube has become very important, because it exhibits quite interesting property that many devices are fabricated with the CN carbon nanotube. And here I have listed carbon nano field effect transistor. Now you have not only carbon nanotube field effect transistor, then we have some molecular devices, then we have some resonant tunneling device. As you said, the name tunneling, again here is a quantum mechanical concept is there, which is makes a new type of devices which we call a resonant tunneling device. Then we have a nano CMOS. Nano CMOS is a MOS where the dimensions are very small. The gate size may be 22 nanometer or less than that. So this is the technology has reached to certain sophistication that the dimension of the MOS devices has become nanometer scale. So that behavior of this MOS will be quite different from a very large bulk MOSFET. So this is a nano CMOS is a new area of nanotechnology. Then you have a molecular uh, devices which are also made with the molecules. Then we have a DNA, another thing which is also used for nanoparticles. And these DNA devices are being also studied very often, but most of the devices which I have listed here, they are consequence of the nanotechnology solutions. Next one. Now this gives you how nanoelectronics, and there is this Moore's law which is applicable to the, I see that they say that after every 2 years the number of devices has become twice, that this is the way it has, I mean you can see that has been grown, that is how the number of this thing transistor goes up and how it changes. And this is the basic law which is used in Moore's, we call Moore's law. Moore's law tells you in an IC you have twice the number in 2 years. Now, you can enhance the number of transistor or devices twice in the in 2 years, and how there is some limit to that. So this has been shown that after a certain time you do not have a validity of Moore's law, and then you have to apply more than Moore's law and things like that. So this is just a presentation which shows how nanoelectronic goes in terms of number of devices, and it's is going up and up. And this is just it. Next one. Now this is the roadmap to the nanoelectronics, and because that is just shows that how the nanoelectronics has developed. That is, now you have the devices, how they are put in the IC circuits. Next one. Now this is the one how the nano devices have grown in the this thing. That's why we say more. Hello. Hello. Sorry about it. Hello. It's got disrupted. Next one. Hello. So it tells you how these number of CMOS has increased, how the smaller and how do you put a smaller how the devices become smaller because you want to put them in a IC chip. And this is the picture. As you can see, the dimensions is naturally you have to put more and more devices, dimensions is going down and down. It has been shown here. Next one. Now these are some of the motivations of by nanotechnology, and this is the how the nanotechnology has been motivation, different motivation has come. And this is the now technology has reached to somewhere in 22 nanometer, and this is the where you can see. Next one. Now this is just a dimension of your wafer has been shown, and that is what it's not that everything goes straight line increase. There is a always there is a change in the projection. So this has been just shown here. Next one. Now this is a curve which shows. So this is the shows the red ones and green ones as the dimensions are going down and down. As you can see, the size of the red ones are going up. This means that innovation overtakes the scaling. I mean, because you have to put a new idea. Hello. Okay, I will call you later. Little bit. So this is just shown you the innovation come scaling is important in the innovation, and this is the way it has been shown. As you can see, the green is the conventional thing. Now you have red portions is coming, which takes account of the different how the innovation is taking place for in developing this one. When you go to the technology of about very this thing, no, not. Now, miniaturization is the objective behind it, and now you have elementary computers are based on soft materials. Now, in nanotechnology, we have an ambition to develop a nano computer, and for nano computer, that main requirement is a miniaturization, that you want to make the dimensions smaller and smaller, and the elementary components are based on soft materials because many soft materials are coming where you are using the carbon nanotubes and this thing. So this is a new dimensions to the development of the nano computer. And now we have a possibility of device operating with one or less than very few, only very few electrons rather than a billion of electrons. That is inside a single electron transistor, and there is a possibility of self-assembly. So these are some of the issues which are quite important for nanocomputer. Next one. Now this is just show this thing. Now one side is the scale. You have a material, solid state material, and this side is a molecular. So you can see nanotechnology has come in the two-prong effect. I mean, two sides. One is the solid state materials, and another one is the molecular electronics. So now a nanotechnology, you can have this possibility that you may have a develop a nano devices with the solid state materials or microelectronics, and then is also possibility of developing it with a molecular electronic approach. So you can have this possibility of solid state as well as molecular development of the nanoelectronic devices. Next one. Now, these are some of the devices which are used in nanoelectronics. Now you can see some of them are solid state, some of them are molecular. Just now I spoken. So you have a CMOS devices, then you have a quantum devices. CMOS devices are based on this thing, nano CMOS devices, and this CNFET. Then you have a quantum dot, then RTD and ACT, and these are then we have these molecular devices, quantum, electromechanical, photoconducting, and electrochemical. So these are some of the devices which are very important. Okay, next one. Now this is just I want to close. I think I have to close the talk. The nanoelectronic solid state devices have a new based on quantum effects. These are nano CMOS and then resonant tunneling diode, single electron transistor, and quantum dots. So these are solid state category of the devices. Then we have a molecular devices that we call it molecular electronics resonant tunneling device, and then you have pintronics, which are also another. So we have a major two categories for future, which have been shown here. I think we have more slides. Maybe we can stop here. You have 1 hour allocated. Now this is the future CMOS. Do I have more time, Bikash? Hello? Hello?
Yes, sir. Yes, sir. Yes, sir. You have, sir. Another 20 minutes we have, sir.
20 minutes.
Yes,
I think I planned it for less than 1 hour, about 1 hour. Okay.
Oh, no problem.
Just
So
show
you
this
can
slide.
continue. You can continue, sir.
So this is the future CMOS, which I have shown here. Current VLSI system, this is used for CMOS, and CMOS is a product of in this nanomaterial. You can put 10 to the power 10 transistors. That was the situation in 2012. Now it has gone to even more. Then you have the example. Today's CMOS gate length is quite small. That is 22 nanometer, and it's even now gone down. So this is the limit of the future CMOS devices. Next one. This is what you call nanotransistor. This is developed with a silicon nanometer. So this is a special nanotransistor which is shown here. You can see this nanotransistor which has been source drain, and then there is a gate which is made with the gold, copper, and gold titanium. So this is the fabrication of nanotransistor. Maybe next one. And this is a simple construction of the thin film nano MOS transistor, which has been shown here. This is a thin film MOS transistor, and this is basically the MOS transistors design which has been done. Next one. Now this shows how the scaling works. As we can scale down the devices, now you can see that once you can scale down the devices, now you can see these are the two graphs here, and this transistor, this is the situation. Now this is the situation with a smaller dimension. This is a larger dimension. I mean, a larger dimension, it won't come down, and it is here. Hello, next one. So this is just once you scale your device, gate oxide dimensions also changes, and these are the history of the gate oxide thickness, how it changes just up to 2000. It's just a demonstration, but you can see how it changes from to this thing. It has come to 100 nanometer in 2000, started with 30 nanometers, the gate length, and this is the oxide thickness, which has been come from 600 nanometer to 2 nanometer. Next. And there is, oxide is thickness is a very big limitation for this nano MOSFET. You have to have a oxide thickness below 2 nanometers. Once you are below 2 nanometer, then there is a lot of problem regarding the fabrication, because you have a lot of pinhole defects, trapped charges, interface structures, dangling bonds, and crystallization. So these are some issues which are arising as a consequence of nanoscale MOSFET, because oxide thickness here you consider is less than 2 nanometer. So this is the thing which is very important. This is the people who are making nanomos. These are the something which appears to be very simple, but it is not that easy. When you want to fabricate something with 2 nanometer, then you have to consider many structural problem like pinholes. Then you have a problem of trapped charges and interface charges. This becomes a problem in the fabrication of the devices. Next one. Now, what happens is that when you have the thickness very small, then you have a lot of leakage. One way to solve the leakage in MOSFET is that you, instead of using the silicon dioxide, which is the most common oxide available easily in the nature, and it has been very commonly used. But when you reach to this kind of dimensions we are talking about, like 2 nanometer thickness, then leakage becomes a big problem. And once the leakage becomes a big problem, then you won't be able to have a device which will work better for your circuit. So for that, what you do is that you use something we call high K dielectric. By introducing high K dielectric, what you have done that you reduce the leakage through the, because this leakage is a consequence of tunneling through this oxide. And once you use this high K dielectric, means like hafnium oxide is a very high K. This generally the dielectric constants were, so if your dielectric constants large, then leakage will be very small, as you can shown here. So that's, if you want to control the leakage, then you have to use these high K dielectrics in a MOSFET. So this is also again a requirement in the nano structure MOS, that you have to have a this high K dielectric placed instead of normal or general dielectric like silicon dioxide. Next one. And this is the way it has been developed, and this is the requirement, as you can see it, that this is the this thing. So this is the development of the so this is the, you can see the development of your MOS over the year. So this is the development of the MOS, which has been presented by Intel. Okay. Next one. Now this is the way the technology has developed, that you can see. Now here from this thing, it's gone like this thing. It has gone from the structural development has taken place, and this thing like that. Okay. Next one. Now there are some challenges or difficulties associated with the these MOS devices. Now these are basically these are listed here. Different this thing difficulties which are
high electric fields and then power applied to the threshold voltage, and these are certain effects. And then we have certain open problems, improve the lithographic. Then you have a challenges like a open problem with the sort of lithograph new ideas behind it. So improve the lithographic technique for this purpose. Explore the possibilities of this thing, nanomolecules. So these are some of the challenges as well as some open problems which you can tackle. So Bikash, shall we stop now? Hello, Bikash.
Okay, sir. Sir, okay, if it's okay for you, sir.
1 hour.
Fine, sir. So
Okay.
you want to stop, sir?
I want to stop because my charge is going on for my mobile.
Okay. Okay, sir. Okay, no problem, sir. No problem.
Thank you very much for you can close it. I think if they are interested seeing some more slides, because my charge is going in there.
Okay, sir. Okay, sir. So I understand, sir. You that I mean the system. There was a problem with your system, and we are actually thankful that despite all the technical glitches, you have somehow or the other managing through your mobile phone, which you are not very acquainted with. So
I don't.
that's very much fine, sir. Because you've taken this trouble at least to ensure that you are able to you have tried to enrich our participants with some introductory as well as some open problems that exist with nanotechnology. So it's okay. We would like to once again thank you very much, sir. Despite your system crashing today, unfortunately crashing, and then somehow or the other managing it through the mobile phone, which you normally don't use, smartphone. But it's I mean we have it's a really I mean we are grateful that you have tried to at least address it, sir. So with this we come to the end of the first session. And we would like to thank our speaker, our honorable speaker, Professor Chandan Kumar Sarkar, sir, who has been the IEEE section 10 vice president as well as the chair of the Calcutta section for almost 6 to 8 years. Then he has been he is the person who actually started with the IEEE Calcutta chapter for Electron Device Society. As well as professionally, he has been the former HOD of the Electronics and Telecommunication Engineering Department, Jadavpur University. He was the former Dean of Indian Institute of Engineering, Science and Technology, Shibpur, which was formerly Bengal Engineering College. He is a visiting professor to many reputed institutes and organizations globally, especially to name a few, Hong Kong University, Max Planck University, Germany, then your Purdue University, US, and many more. He has also been, resource person as well as a lot of technical program heads. He has headed for IEEE as well as other societies in devices. His primary work, which was on the electron transport, which he carried out at Oxford University way back in the year 1979 to 1981. And further, he was the one of the visiting chairs over there. With this, sir, with your illustrious career and your experience in the field of devices and the current modern day nano devices and semiconductor industry, we are really privileged and honored to have you as a speaker. And we feel that your guidance and your experience and expertise in the field would definitely benefit our audience and the participant. Now, with this, sir, with your due permission, can we have few questions from the audience?
Sure.
Yeah. So I request the participants, if they have any question to be asked to sir, they can raise their hands. We'll unmute you so that you can go ahead with your question, please. Yes, our guest, I think Miss Abha, you can go ahead with your question. We have permitted you to unmute yourself.
Hello.
Yes, ma'am, you're
Yes.
audible. Please go ahead with your question.
Good afternoon, sir. First of all, I am very privileged that I listened, sir. I am also doing work on electronic devices. I did my PhD from KwaZulu-Natal University, South Africa. I have one question that right now the work is going on in quantum mechanics and quantum at 5 nanometer technology. So what is the possibility to fabricate the device over the 5 nanometer technology? Is
I
it
think this
possible
facility.
during these days?
No, as you said, the approach is there. The people are approaching that they want to fabricate, but I don't think it can be fabricated in India. Even we don't have a technology very well, even 22 nanometer, which is come very big way in the Western world. But I would say that it is good idea to keep the ambition high. So surely you can, but then fabricate things of that in that range. The things and physics becomes quite different. And I think before you fabricate, you have to understand what's the physics behind the whole thing. I mean, how the device physics will work out.
Sir,
As
if
you
we
can
use
see
the
that
QME technology about that, then it will be successful for that.
please you repeat your question. Hello?
If we will use the quantum confinement and quantum mechanical engineering in that on the channel length, then if it will be possible for fabricating the device, or we must first go through that research and do the analytical modeling for that channel length.
I think you are very much right that you have to understand the first of all the physics of the device, then only you can fabricate, and you have to properly simulate the device, because when you reach to that kind of level, and I think simulation of the device will be very important, because from the simulation you will understand what is the behavior of the device, because sometimes you have a model but the actual performance of the device is quite different. So I think it's a good idea to keep that kind of ambition, but which is most important thing is that you try to understand the physics of that device. Okay.
Okay. Okay, sir. Thank you so much.
Thank you, ma'am. Now, Ms. Sashi, I think you had raised your hand. If you can just go ahead with your question. We have allowed you to unmute yourself. Yes, Miss Madam Sashi, as I can see the name, we have allowed you to unmute yourself. Oh,
Yes,
so
sorry.
sorry, sir.
Yeah.
That's what I was saying, sir or madam. Please go ahead with your question.
Good morning, sir. I'm Dr. Shashikant. We both, like me and Abha, both we were working together in South Africa, and we followed several research articles from Professor Sarkar. Professor Sarkar, I have one question regarding this structural modification in the device. Sir, what you look for the possibilities in the other structural modification in the MOSFET in the current edge of range of dimensions, sir? We can see that several structural modifications are into the MOSFET is going on. So what you look for, what you think, sir, as a experienced person in this field, that what are the possibilities that we are looking in the other structural modification in MOSFET, sir? Sir, am I audible, sir?
Yes, I can hear. Can you hear me?
Yes, sir. Yes, sir. I can hear, sir. Yes, sir.
MOSFET, I'm not very sure. I think this is a very ambitious to think, but what still we have a lot of possibilities with the new quantum devices, such as I've shown in one slide, like the quantum. There are some new devices you can fabricate with a quantum. And most important is that behavior like a single electron transistor and resonant tunneling diodes. These devices will I hope that provide some new fabrication possibilities will be there, and then come out with some new, particularly is something which is very important. And then there is a modification of MOSFET, as you know.
Yes, sir.
Sir, if you allow, can I add on to that, to Dr. Sashi's question?
Yes, sure.
Yeah. Dr. Sashi, like I'm not I'm just a amateur in this area, but to add to your question, like when you say the modification in the structure regarding the MOSFET, the current MOSFET technologies, if you try to understand, we have a lot of new geometries that has been incorporated and has been presented. Especially, you can see the double gate all around, and triple gate MOSFETs. Plus the FinFET, which is actually a very promising device currently. So this FinFETs now furthermore, like, because the issue of these FinFETs was addressing the issue of tunneling. Now, when we talk about these FinFETs, the FinFETs was trying to address the issue of tunneling, which was very predominant in such nanoscale devices. But again, further reduction of these devices was getting is getting actually difficult. One primary reason is because we are still working on silicon technology. So this silicon technology, the scaling of this silicon material is becoming difficult. The idea is, like, mostly we are trying to incorporate many low dimensional materials of either group 3, 5 or even TMDs, that is transition metal dichalconides. So the low dimensional forms, that is either in the 2D form, that is your 2-dimensional form like your graphene or your molybdenum disulfide or your palladium selenides, as well as 1-dimensional forms in the form of your this nanotubes, whether it is carbon nanotubes or you have other tungsten nanotubes or boron nitride nanotubes. These are quite a few promising materials. So there are the research are being carried out globally at different places where we are trying to address the issue of scaling primarily. So when we look into the picture, one another thing when we come to this, when I was talking about this nanotubes, that is 1-dimensional materials, your nanowires are also quite promising. So nanowires, whether it is a carbon nanowire or any other
even graphene.
Yeah, so these are certain things which people are working. So although this single electron transistor is also a big area of research, but they again face with this quantum mechanical effects of your inter atomic or your vicinity. So there we are actually trying to work with many things at the same time. Like, I mean, definitely many people are working in different domains. So maybe we are trying to optimize the things which could be best possible for future applications. So I feel that the application of modern or say the latest nanomaterials in their low dimensional forms would be quite promising to scale down the devices to improve their geometries as well, so that whatever the short channel effects that are encountered in the this nano CMOSs could be addressed. So this is something out of a little bit of study that we had. I feel that these has the prospect of doing things ahead, sir.
Great. Thank you very much, sir, for the detailed explanation. Professor Sarkar, thank you very much, sir. Yeah, thank you.
Tunnel field effect transistor, which
Yes,
is
sir.
also and that can be improved. The tunnel field effect transistor is again another device which is now coming big way, challenging the MOSFET.
Yes, sir. Yes, sir. Thank you very much, sir. Thank you very much, sir. Thank you very much for your answer.
Thank you. Thank you so much, sir. We can have a couple of more questions if we have any more participants, if they have any more questions. Okay, sir. Sir, I think we have overshot our time. So I think once again, I'd like to thank you, sir. And really, from the bottom of our heart, we are very grateful to you that you have taken the trouble to at least present through the mobile phone, which, as I again repeat it, you are not really acquainted with the smartphones. You have been using simple feature phones all throughout, as simple as you are in your personal life also. So we are really grateful to you, sir, and thank you once again for your for sparing your valuable and very your time that you have shared with us with your expertise and your experience. I hope the participants must be benefited with your talk. Thank you once again, sir.
Thank you very much. I thank all the participants for their participation and interest in my talk. Thank you.
Thank you, sir. Thank you. Yeah. I with this I like to inform that the session this the first session in the morning is will be ending it now. The next session would start at 2 o'clock, and it will be we'll have a talk by Mr. Pragnjit Datta Roy, sir. He is from Qualcomm, and he has a vast experience on SoCs and chips. So I believe his talk also would be definitely interesting and beneficial and enriching to all our participants. So hope to see you back at 2 p.m. I request you all to join at least 5 to 10 minutes before the session starts. So thank you, everyone. Have a good day.
Thank you, sir.
No, of course, I charge the